Okay, this is Physics 1B for let's see, October 11th. Today we're going to be talking about. Let me zoom in a little bit so you can read those better. I'll have to make everything else really small, but that's okay. So today we're talking about equations of state, the ideal gas equation, which some of you may have heard before. We'll do quite a few problems with that. If we have time at the end, we'll talk about PV diagrams and these other topics here. But mostly what we'll be talking about today is what the ideal gas law is and how to use it by looking at some problems. Okay, so let me grab this. Sorry. Okay. So what is an equation of state? Oops. Equation of state. An equation of state is something that can describe, if you have a system, let's say a system that could be like, a solid, like a planet, or it could be a gas, like the gas in a room or something like that. An equation of state could tell you certain qualities of what's happening at one moment in time, and it can allow you to predict what's going to be happening in the future based on changes to those quantities. So, the type of quantities that we're going to care about are going to be like macroscopic properties of the substance. So for a gas, it's going to be things like pressure, volume, temperature, and amount of substance. So the question really is, like, an equation of state is basically something that describes how macroscopic properties of the material evolve over time. This is kind of similar to the way in Physics 1A when you learn about a projectile. You learn that you can know, if you know where it's located and you know what its initial velocity is and you know what forces it's subject to, so you can figure out its acceleration. Then if you know those quantities, you could figure out where it's going to be in the future, right? And you could even describe a path, through the air that will show you the position effectively as a function of time and space, right? So an equation of state does a similar thing for something like a gas, but with a gas, because it's composed of so many tiny little molecules that are all doing very different things, they have different velocities. It's better to talk about the macroscopic properties, okay, not the microscopic properties would be like the mass of an individual molecule or the individual velocity or location of a molecule. But the macroscopic properties are things like, as I said, pressure, temperature, volume of the substance, how much space it occupies, right? And then also little n, okay? And n is going to be the amount of the substance, okay? N is going to be the number of moles. And the way that you can count the number of moles of the substance that you have, shift this down just a little bit here. Maybe some of you can tell me, how can you figure out the number of moles of a substance that you have? Let's say there's some other quantity about the substance that you can measure. Like, let's say that I give you a piece of iron, and your job is to tell me how many moles of iron there are. How could you do it? Assuming you had some equipment that you could use. You get some little piece of iron. What could you do to find the number of moles? Anyone know? There's a lot of people typing. You can go ahead and say it. How would you use it though? Okay, Mustafa's. Yeah, that's right. You can use weight and molar mass. So? What do? You measure the weight, right? And then from the weight you get the mass. So if I know the mass, and I know the molar mass, so let's say that little m represents the mass of the substance, and we use this symbol, capital M, to represent molar mass. So molar mass is kind of exactly what it says. It's, how much mass do you need to get 1 mole, pretty much. And this is found from the periodic table. So you need to go and you need to look up, let's say that what we have here is, let's say the mass is 1 kilogram, okay? And let's say we're talking about iron. So if we look up the molar mass for iron, I can't remember which, I think one side of the textbook has periodic table. Can someone look it up for me too, if you, I think you do. I thought there was a periodic table in here. Maybe it's just one of the appendices. Can one of you look up the molar mass for iron? Oh, you guys got it. Good. Let's use the first one there. 55.85. And that's in units of grams per mole. And if you just look at what the units are, it tells you everything you need to know about it. It's basically just a conversion factor from mass to moles. Okay. So we could find that if you have 1 kilogram of mass, what do? You just take, you just do the mass divided by the molar mass, should give you the m's, right? This would be the equation, I think, right? M over m would be equal to little m. Because then if you do 1 kg or divided by, so it's going to be 1 mole divided by 55.85 grams. But then we also have to convert from kilograms into grams. So we multiply by 1 kg, 1,000 grams. Okay, and that would give us the number of moles. Where's my phone? Okay, you're all gonna have to calculate it. It's basically 1,000 over 55.85. 17.9. It's a lot. It sounds like a lot, but it's just, what is a mole? That's also what we have to talk about. So 17.9, almost exactly 18 moles. Is that right? So, and then what's the unit? It's just moles. So mole is the amount of a substance. It's the, I didn't realize I was going to need to do all this stuff before we started. So a mole, when you say you have 17.9 moles, that describes just how much of the substance you have. That's the unit, is moles. And then Matthew mentioned Avogadro's number. We might as well mention that too. So Avogadro's number is 6. I think we talked about this at least once in this class, right? And the units for this one are the number of atoms per mole. So if you take this number of moles, and you multiply by Avogadro's number, that gives you the number of atoms of the substance that you have. Atoms. There's one other thing you can do with this. Well, there's a lot of other things you can do with Avogadro's number. You can find the mass of a single atom as well, right? How would you do that? How would you find the mass of a single atom using this kind of information? Any ideas? How would you do that? You can use the symbols that we have here. Maybe write an equation or something. Mass of a single atom. Really, if you think about it, all you really need to do is to just find a conversion factor to get atoms per gram, or grams per atom, sorry. You can see any way you could put together some of the numbers that are on the board here, or on the screen, to get grams per atom. How could you get grams per atom? Any ideas? How could you get grams per atom? .5 divided by, yeah. So in terms of symbols, that would be, yeah, I know what you, that's okay, I know what you mean. In terms of symbols, that would be capital M, right? Divided by Avogadro's number. And that should be equal to the mass of an atom. I'll put M sub atom. And of course, you know, not all atoms are the same, right? An iron atom weighs more than like a boron atom or something like that. So these equations are like pretty helpful for, you know, just different things. Like this one's pretty helpful. This one's really helpful here too. So just something to keep in mind when you're doing problems in this section and for the rest of the semester as we talk about, because a lot of what we're going to be talking about from now on is going to be thermal kind of properties of things, and you know, you're going to need to understand how to do these conversion factors from time to time. That's all they really are. They're just little conversion factors that you're doing. Okay, so let's get into an equation of state then, now that we know kind of so equation of state again is, to refresh, we want to talk about how macroscopic variables such as pressure, temperature, volume, and then this new one, which is number, because we've probably talked about pressure, temperature, and volume up already, but this is kind of the new one, the number of moles. So now we kind of want to describe how these properties change over time. And so I'm going to give you two of them. This first one here this would be for a solid. This is for a solid. This would be the equation of state for the solid. And it has some things that you've seen before. For example, the first piece right here, if you don't look at that part there, the first part right here is from the volume expansion equation that you've used before, right? Basically says, you know, if you look at this term right here, V naught times beta times T minus T naught, that's the same as the volume expansion equation. And then it's just been turned into an equation to get the volume, you know, given the initial. So you see what I mean? This is a lot like, here, let me just put, what's the equation of state for a baseball that's thrown through the air? Well, it's this. It's delta y is equal to, and I'll even write it in a similar way. It's y is equal to y initial plus v initial times t, and it's really delta t, and then plus what? 1/2 acceleration in the y direction times delta t squared. So the first few terms are really similar. You have like a quantity. You want to know how it evolves over time. So what do you need to know? You need to know the initial position. You need to know the initial velocity, and then you have to tell me how long after the initial measurement do you want to find it, right? And that kind of looks pretty similar to these terms right here in my mind. Think of the delta t here as temperature, but this is time, and you have your initial volume instead of your initial velocity. Anyway, so they're very similar kind of concepts, because in physics that's kind of always what we want to do. I think in science in general, often it's always what we want to do is we want to know, if you know what's going on right now, can you predict for me what's going to be going on tomorrow, right? That's what the weather's all about, right? It's like, can you tell me what's going to be happening tomorrow? And ultimately it's, you know, something like what's the weather like tomorrow boils down to a lot of complicated individual equations of state, like stuff like this. They mention here that there's a negative sign, so the volume is now going to depend on kind of two things here. It's going to depend on temperature and pressure in this case for the solid. And it says there's a negative sign here because when you increase the pressure, there's a decrease in volume, whereas when you increase the temperature, there's an increase in volume because it expands. So, yeah. You have any questions so far? Okay. So let's talk about the equation of state that we're going to be using the most in this class, which is for the ideal gas. Oops. So I guess what we should say is about what an ideal gas is first. Ideal gas. An ideal gas is like this semester's version of like the frictionless pulleys and massless pulleys and stuff like that. It's basically a gas that where we're going to make some assumptions about what's going on with it. We're going to assume that it kind of none of the molecules ever really interact with each other. That the molecules tend to be very far apart from each other, and it's. I think we're also going to assume that it doesn't actually exchange energy with its surroundings. Maybe we won't always assume that. That's probably not true. But that's what an ideal gas is. And this down here, which we want to kind of try to understand for the next few minutes here, is what we call the ideal gas equation. And if we follow through what's said right here, we'll kind of get to an understanding of what that means. But what I'd like to do is take this picture that's over here, and we'll do a little interactive thing with it. So in this picture, what you have is you've got some kind of a gas that's contained here, and there's a gauge to measure its pressure and a gauge to measure its temperature. And then we have something to heat it up. And also at the bottom, there's a piston which can allow the volume of the temperature to increase. And then finally, there's something where you can either add or take away gas. And the goal of something like this would be to be able to study how these different variables depend on each other. How does pressure, volume, temperature, and number of moles, how do they depend on each other? And obviously you can see the way they do down here in this equation, which a lot of you have probably seen before, PV equal to nRT. But we're going to look at this, which, can I full screen this too? I guess I can. Don't need that button. Okay, so I think this should be able to do the same thing. So this is movable, and I think it'll move by itself if the system expands too much. There's currently no gas in here. This just allows us to open up the gas, and so it's basically the same thing. We have something to measure temperature, something to measure pressure, something to add heat or cool it down if we want to, and then I guess we can change what type of molecule we have in here or something like that. Oh, it's either we do light or heavy. Okay. Anyway, let's just put these heavy ones in here. Do we want to do anything else? Okay. Looks like we can also hold some things constant if we want to. Looks like we can't hold these constant for some reason. I don't know why. Maybe because it's 0. Okay, so you pump gas into here. You can see what starts to happen. Right now, is the pressure. Let's see what happens with the volume. I don't know if this is going to change or not. So the pressure goes up. It's going to stabilize eventually, I would assume. Temperature here is now at 300 Kelvin. Pressure's changing a lot, huh? It's interesting. I wonder why that is. Okay, so if let's make some really quick predictions right here. What do you think is going to happen if let's do this. Let's hold the volume constant for now. What do you think is going to happen if I heat it up? What's going to happen to the pressure? What's going to happen to the temperature? Should be pretty obvious. Pressure is going to go up. Yep. Both should increase, right? Because a hot gas obviously has a higher temperature, and if it gets hot, then the molecule should vibrate more, so the pressure should increase, right? Is that obvious? I don't know if it's obvious, but I think you probably have some experience that tells you that's true, right? So there you go. You heat it up, and the pressure goes up. All right, now the temperature is at 651 Kelvin. The pressure is at 100 atmospheres, almost exactly. So that tells us that if you add energy to a system that has the volume held constant, then the pressure and the temperature will both increase. Okay. So what else could we do? We could Okay, I guess I can ask this. If I click on, I don't know what's gonna happen. If I click on nothing here and let the volume expand, wouldn't you expect that this thing would expand? Let's see what happens. No, I wasn't sure about that. Okay, so now if I let the volume, what can I hold constant? I guess we could hold the temperature constant. How would you hold the temperature constant? Oh, but then I can't increase the temperature. That's not gonna help. I thought it would let me do that. It won't let me do that. Interesting. What does this mean? Volume, temperature, pressure with V with the arrows up and down. What does that mean? Hold pressure constant but allow volume to change? You think that's what that means? Let's see what happens. No. Oh, is this pressure and volume? Oh no, it is loud. Okay, that's what I thought it was going to do, but that was confusing the way that it said that. Okay, so now I get it. So this is saying that hold pressure constant, but temperature increases, pressure increases too. Okay, so does this one make sense? So if I have pressure of 150 atmospheres or whatever, if I say that I want to keep the pressure constant, but I want the volume to change, if we cool it down, what's going to happen to the volume? Assuming we want the pressure to be the same. Yeah, it should decrease, right? There it goes. That's something that you can kind of easily test in a way by taking a balloon. If you take a balloon, you blow it up, and you put it into a refrigerator, then the balloon will get smaller after a certain amount of time. Yep. So if we heat it up, the volume's going to increase here. And again, this is because it's specifically holding the pressure constant. So the only way to hold the pressure constant is to let the volume go up. Temperature also is going up. All right. What else can we do here? If we hold temperature constant, no, we can't really change anything then. Oh, well, that's another thing we can change, is we can increase the amount of moles of the substance. I wonder if you hold temperature constant and you do this, what's going to happen? The pressure, okay, that's what's going to happen. Okay, return lid. What else can we do here? So the whole goal of this is kind of just to see how these things interact with each other. And we saw a few things already that as you add energy, both pressure, temperature, and volume all want to increase. And as you add these molecules, you can see that pressure increases. But the temperature isn't really increasing very much. And by kind of putting all those things together, you get this list here, which says that the volume is proportional to the number of moles. So that if we double the number of moles, keeping pressure and temperature constant, the volume doubles. The volume varies inversely with the pressure, so that if you double the pressure while holding temperature and number of moles constant, that the gas compresses to 1/2 of its initial volume, which means that pressure times volume is a constant when an interior constant. And then finally, that the pressure is proportional to the absolute temperature, so that if you double the temperature, keeping the volume and number of moles constant, then the pressure doubles. This is another reason why absolute temperature was so important, because of the fact that there's a 0 on the absolute temperature scale means that when you go from 100 Kelvin up to 200 Kelvin, you're actually doubling the temperature. And what they're saying here is that if you double temperature while keeping volume and number of moles constant, that the pressure doubles. So I wonder if we can actually see this. So it's saying keeping volume and number of moles constant, if the pressure doubles, the temperature should double. Let's see if that's true here. Okay, let's see if we reset and pump some of these things in here. So what do we have to do? We have to hold volume constant. Okay. It says if we double the temperature, keeping the volume and the number of moles constant, then the pressure doubles. Okay, so that's saying that if we take the temperature from 300 up to 600, right? If we go from 300 up to 600, what should the pressure be then? If I change this from 300 to 600, what should the pressure be? Let's see if everyone's following along. Yeah, about 112. It should double to about 112. That's right. Now, is atmospheres an absolute unit too? It is. You can have 0 atmospheres. So whether it's in pascals or atmospheres, it should double. So we're looking for like about 112. Let's see what happens. I'm gonna try to get to 600 here. I don't know how slowly I have to go. A little bit faster, I guess. Okay, that's pretty close. There it is, 113. It's not exact because... Oh, but I can cool it back down. Oh, I shouldn't have been so careful. There it is, almost 112 at 601. Okay, so that seems to work, which isn't too surprising because it's a simulation. So it's working off of this equation, but still. What's the other ones that we can test with this? Volume is proportional to number of moles. If we double in by keeping pressure and temperature constant, volume doubles. So that would be pressure and temperature held constant. We have to double the number of moles. Is it counting the number of moles? Oh, they're right here. I mean, this isn't really number of moles, it's number of particles, but it should still work. If we double this, the volume should double, right? That's what it's saying, right? Number of moles, number of particles. It doesn't matter how you count it. If you double them, it's saying that the volume would double, right? So the volume here is... Oh, that's what this is for. To measure the width. So now it's 10 nanometers. So if we... 483... You see how it's, why is it doing that with the ice, by the way? Oh, but the volume's not changing. I guess it was thinking this needs to be fixed. Is it because I pushed that? No. Huh. We're keeping pressure. Oh, this is, I pushed the wrong button. I think it's this one. That's what I was supposed to, okay. So let's cut this in half. And then I can still use this, right? Yeah, so it's saying that if I go from 433 up to 866, that it should exactly double. And it looks like it is, because it's up to 10 now, because it was 5 and then now it's 10. Okay, so that's just a way of kind of like visualizing it, I think. But if you put all that stuff together, you end up getting this equation right here, which says that pressure times volume is equal to number of moles times the ideal gas constant multiplied by absolute temperature. And in this case, the T, the temperature, we've been kind of, I would say maybe sloppily using Celsius from time to time up till now. With this equation, you have to use Kelvin temperature. It won't work otherwise. Otherwise, you could have, you could put a 0 in here if you had 0 degrees Celsius, but we're not going to do that. One thing that gets often used by this equation is that if the number of moles is a constant, then we can have, I don't know what you'd call this, but it's the version of this equation that gets used really frequently. If you know the pressure, the pressure, volume, and temperature of a gas at one point in time, that should also be equal to this quantity here. You can say that the pressure times the volume divided by the temperature is a constant. So this whole thing is basically a constant. You can see here it's equal to n times r, basically, if you're interested what that means. And what's r? So r is the gas constant. If you've taken chemistry, you've probably seen it before. If you took chemistry, you probably used this one, 0.08206 liter atmosphere over mole Kelvin. An equivalent version that we'll use in this class is this one right here, 8.31 4462, whatever. We'll just probably use 8.31. You can use as many of these digits as you want to, I guess. Joules per mole Kelvin. So liter times atmosphere is the same as joules. Not the same, sorry. Excuse me. Liter times atmosphere is not the same as joules. They're both units of energy, though. It is important to understand that if you use the one on the bottom, you have to write your volume in liters, and you have to write your pressure in atmospheres. If you use the one on the top, you have to write your volume in meters cubed and your pressure in pascals. Okay, so I guess I should write that right here. For this one, you use pressure in pascals, and you use volume in meters cubed. And then for this one, obviously, you can see like there's liters here, so volumes in liters and atmospheres is going to be your measurement of pressure. We can use the equation it's not this one. It's the other one. This one, little m over big M is equal to N. Let's use that equation. So we have pressure times volume is equal to nRT. And up above, the equation was that number of moles is equal to the mass of the substance divided by the molar mass. So if we plug that in here, PV equal to little m divided by big M RT. Now what we can do is we can put the density of the gas in now, I think, by, if we multiply the molar mass to the left-hand side and we divide by volume, then this equation becomes, we'll write it like this: pressure times molar mass divided by R times T is equal to the density of the substance. Okay, we're going to use this a little bit later here. Okay, so before we go into solving some problems with this, does anyone have any questions? Have a lot of you seen this before? Okay, so let's see how this first problem I think is pretty easy. So I think maybe it might be a good way for you just to test to see if you understand the equation. So I'll just write it right here. So it's pressure times volume is equal to nRT, right? See if you can solve this problem. What is the volume of a container that holds exactly 1 mole of an ideal gas at standard temperature and pressure? Standard temperature and pressure is defined as temperature is equal to 0 degrees Celsius, pressure is 1 atmosphere, which is that. So the question is, what is the volume? So we're finding volume here. And let me grab the 2 versions of these, copy, paste, so you have that. Let's just do the calculation real quick. I'll come back and do it with you. I'll give you a minute. I have to refill this water real quick. BRB. Whoops. Was that enough time? How much time was that? That was probably like 30 seconds. Okay, so Noah got an answer. Maybe I'll give you like 30 more seconds. Okay, that's good. Brain got an answer that's in a different unit, because this can be done both ways. Okay, so yeah, that's all we have to do. Just rearrange this to solve for volume. Number of moles is 1 mole. can use either version of this that we want to. So if we put, for example, 8.31 joules per mole Kelvin, multiply by temperature, which we have to use this one. And we divide by pressure, which is 1 atmosphere. So if you use 8.31, then down here you have to put in pascals, 1.013. And that's because pascals has, remember, 1 pascal is 1 Newton per meter squared. So there's a Newton in here, and then a joule has a Newton in it as well, because joule can be Newton meter. And when you do that, you end up getting meters cubed out of this. That sounds like everyone's getting 0.0224 meter cubed. Or if you do it the other way, you'll also get 22.4 liters. So this number, okay, those of you that have taken chemistry, this number is kind of meaningful for chemistry, right? I mean, it's obvious. It's the volume of an ideal gas at standard temperature pressure, right? This is I think. Okay, I'm misremembering this. I'm gonna say something. You gotta tell me if this sounds right to you. I think this is right though. I think this is one of the first things that some of the chemists that were studying, when they didn't know what this law was already, one of the first things they noticed was that if you have, when you have chemical reactions that involve gases, that the gases would always have whole number multiples of this number or something like that. That if you had like H2O and you somehow turned it into its constituent molecules, that you'd have, let's say, like 44.8 liters of hydrogen and you'd have 22.4 liters of oxygen. Is that right? That almost starts to sound like it can't be right. That can't be right. Can it? Is that right? I don't know. Definitely they noticed that the volumes of gas that they were getting out of these experiments would have whole number multiples. That part's true, right? Does that part sound right to you guys? This has been a long time since I studied this. Anyway, it is interesting. What this is basically saying is that if I have a mole of... Yes, that was in the chem textbook, what I just said. Okay. The part about the whole number multiples, or about this number, 22.4, being important. I don't think the number was important. I'm trying to think about this, but if you have a mole of oxygen or a mole of hydrogen, it's going to be... Yeah, the whole number multiples thing, okay. If you have a mole of oxygen or a mole of hydrogen, it's going to have the same volume. It'll always be 22.4. Okay, so that's a pretty easy one. Let's go on to one that these two, it gets a little bit harder. These never get that hard, but you know. I guess the very last one we're going to do here is kind of hard. So let's look at this one here. I'll give you also time to look at it as well. All right, so in an automobile engine, a mixture of air and vaporized gasoline is compressed in the cylinders before being ignited. A typical engine has a compression ratio of 9:1. That is, the gas in the cylinders is compressed to 1/9 of its original volume. The intake and exhaust valves are closed during the compression, so the quantity of gas remains constant. What is the final temperature of the compressed gas if its initial temperature is 27 degrees Celsius and the initial and final pressures are 1 atmosphere and 21.7 atmospheres, respectively? Okay, so where did it say it? The intake and exhaust valves are closed during the compression, so the quantity of gas is constant. Okay, so if we know that the quantity of gas is constant, how do you all think we should approach this problem? It's obviously an ideal gas law problem, but should we do it like we did the last one? Or do we need to do something different? What do y'all think? Yeah, that sounds right. Okay, so since the gas, the number of moles is constant, so N is constant, that means we can do this pressure 1 times volume 1 divided by temperature 1 is equal to P2, oops, P2V2 over T2. Okay, so now we have to also just kind of label what these quantities are. So over here we've got, okay, so initial temperature, so our goal is final temperature, so T2 is going to be what we're looking for. T1 is 27 degrees Celsius, so we're going to have to do 27, we need to add to that 273, so you're going to get, is that 300? 300 Kelvin. The initial and final pressures are 1 atmosphere and 21 point. Okay, so pressure 2 is 21.7. You can all, if you know how to do this already, you can just do the problem yourself right now. I'm just gonna keep writing this stuff down. Pressure 1 is 1 atmosphere, and we were told that the gas in the cylinders is compressed to 1/9 of its original volume. So for example, if I said that V1 was equal to just, I don't know, we just give it a symbol, just call it V, then V2 would be equal to, what would it be? V over 9 or 9 times V? What do you think? What's V2 going to be? Is it going to be the initial volume over 9 or the initial volume times 9? V over 9, yeah, that's right. Okay. You could also, by the way, if you really wanted to here, you could just say let the volume be equal to 1 liter, and then, or even easier, let the volume be equal to 9 liters, and then this would be equal to 1 liter. That would work too. Doesn't really matter. If you don't want to call it V, you can call it 9 liters, and this would be 1 liter. Okay, so now we just need to solve for T2. So what I would do, just like we kind of always do with these problems, just solve for T2 out of this equation. So that means that T2 is going to be equal to T1 times pressure times volume 2 divided by pressure times volume 1. Yep, because we basically just, these two change places, and then multiply this one right here. And then if we plug all those things in together, P2 was, what, 21? Okay, so 21.7. Wait, let's start with this one. T1 was 300. P2. Volume 2. Let's just make it 1 liter. That seems like it's the easiest thing to do. Divide by pressure 1, which was 1 atmosphere, and volume 1, which we're just going to use 9 liters. Okay, so you can see that it's going to be something like a ratio of 22 over 9 multiplied by 300. So not quite like 2.5 times as much, but yeah, about 2.5 times as much, right? Something like that. So 300 times 21.7 divided by 9. $7.23. You all get the same thing? So not very hard. Just have to kind of notice that it's one of these kind of problems. So you do this. Does anyone have any questions? Okay. What time is it? Okay, maybe we do this this one and then take a break. An empty aluminum scuba tank contains 11 liters of air at 21 degrees Celsius in one atmosphere. When the tank is filled rapidly from the compressor, the air temperature is 42 degrees Celsius and the gauge pressure is 2.1 times 10 to the 7 pascals. What mass of air was added? Air is about 78% nitrogen, 21% oxygen, and 1% miscellaneous. Its average molar mass is 28.8 grams per mole. Okay. So what we know... Should I just let you all look at this one for a little bit? Should we take like an extra long break and let you try to solve it? Not extra long, but I mean, like, just take a break starting now, and that way, like, you can work on it, and then... Do you want to do that? Let's do that. Okay, so we're going to break until, like, 10:50. That'll give you, like, 17 minutes, so you can try to solve this. Maybe that's too much time. We'll just take a break until 10:45. And even when we come back, I'll maybe give a little more time, but I'll just say some things. So just try to solve this problem. And when we come back, we'll talk about it.